In this video, we're going to talk about orthogonal matrices. An orthogonal matrix is a square matrix say A, such that A is invertible and A transpose is equal to A inverse. So an orthogonal matrix is a square matrix that's invertible, and normally to find the inverse of a square matrix, it's a bit of a pain. You have to row reduce the matrix, but for an orthogonal matrix, you can just find the transpose. Well, if A transpose is equal to A inverse, then I can multiply both sides on the left and right by A, and I get A transpose A is the n by n identity matrix, and A times A transpose is the n by n identity matrix. And if a matrix satisfies either of these inequalities, either of these equalities, A transpose A equals the identity, or A transpose is the identity, then it must satisfy the other one. That's a fact that we talked about before. This fact that if you have two square matrices, if you get the identity matrix in one order, then you're going to get the identity matrix in the other order. So you just need to check that A transpose A is the identity, or A transpose is the identity. If the matrix satisfies that property, then A is invertible, and its inverse is A transpose, meaning that A is orthogonal. So, for instance, is this matrix 1, 0, 0, negative 1 orthogonal? Well, as we just explained, you only need to check that A transpose times A is the identity matrix. If A transpose A is the identity matrix, then A is orthogonal, otherwise it's not orthogonal. So let's figure out A transpose times A. Well, that's A transpose is going to be this. Actually, in this case, A transpose is equal to A. And if you multiply A transpose by A, you do in fact get the identity matrix. So A is orthogonal. On the other hand, if you take a matrix like A equals 0, 1, 1 half, 1 half, okay, if you calculate A transpose A, that's going to be this matrix times A. And if you calculate what you get this, which is not the 2 by 2 identity matrix, so A is not orthogonal. So pretty simple to tell if a matrix is orthogonal or not. Okay, let's look at some properties of orthogonal matrices. Let's look at the columns of an orthogonal matrix. So it turns out, there's a theorem, that A is orthogonal. So A being a n by n matrix, so maybe I'll just say an n by n matrix is orthogonal if and only if, that's precisely when the columns of A, so an n by n matrix A, the columns of A are orthonormal. Remember, that means that they have a unit length and they're mutually orthogonal to each other. If you take two different column vectors, their dot product is 0. let's prove this. So let's prove that if you have a matrix that's orthogonal, then the columns are orthonormal. So suppose that A is an n by n orthogonal matrix. Well, we want to take, then A transpose A is the n by n identity matrix. So let's say that A has columns v1 through vn. Then A transpose is just going to be the matrix where the rows are the vi transposes, right? Because I'm thinking of these vectors as column vectors, so the corresponding rows will be the transpose. And then if you multiply that by A, you're going to get the n by n identity matrix. Well, the ij entry of this product, is equal to vi transpose times vj. Right? You take the ith row, okay, and then multiply that by the jth column. That's what gives you the ij entry. And since you get the identity matrix, since A transpose A is the n by n identity matrix, what does that tell you about the ij entry? The ij entry is maybe I'll just rewrite this to make it a little neater. I comma j entry is 1 if I is equal to j and 0 if I is not equal to j. So that tells you that vi transpose times vj is 1 if I is equal to j and 0 if I is not equal to j. Well, that's precisely what it means for your vectors to be orthonormal. So the columns of A are orthonormal, right? Because if I is not equal to j, so if they're different column vectors, they're different columns, then the dot product needs to be 0. And if they're the same, if I equals j, then the dot product is 1, meaning that the length of the vector is 1. So these are unit vectors that are mutually orthogonal with each other. That's what it means for the columns of A to be orthonormal. And conversely, suppose that the columns of A are orthonormal. Well, then that tells you that, see, you're basically just reversing the order. Vi transpose dot vj is equal to 1 and 0 if I is equal to j and if I is not equal to j, respectively. That's what it means for the columns of A to be orthonormal. And that tells you that if you take A transpose A, you get precisely the matrix whose ij entry is 1 if I equals j and is 0 if I is not equal to j. And that's precisely the n by n identity matrix. So that's the proof. Okay. It's just, the main thing is this, is recognizing that when A transpose A is the identity matrix, that's really the same as saying that when you take the dot product with the ith and jth vector, you get 1 if they're the same and 0 if they're different. And this is another quick way to see that the second matrix is not orthogonal, because this column does not have unit length. Right? The length is root 2 over 2. And this one, for the first one, the columns are perpendicular and they have unit length. So A is orthogonal. That's a way to tell if it's orthogonal without having to actually multiply the matrices. But of course, it's not too hard when you have a 2 by 2 matrix to just multiply A transpose and A and see if you get the identity matrix. All right, now let's look at another property. So another property of orthogonal matrices is that the determinant, well, oh, by the way, an orthogonal matrix is often written as Q. So let's use Q for an orthogonal matrix. The determinant is either plus or minus 1, so if Q is orthogonal. Okay, the reason for that is because, so again, we have to use the fact that Q transpose Q is the n by n identity matrix. Well, Q and Q transpose are both n by n matrices. And we know this fact about the determinant, that the determinant, I have a product of two matrices, two square matrices, and I can say something about the determinant. The determinant of this product, Q transpose times Q, is the product of the determinants of the individual matrices, right? And I just want to remind you that this is an equation involving numbers. This first one is saying that when you multiply these two matrices, you get the identity matrix. This is saying that this number, the determinant, is equal to this number, the determinant of Q transpose, times a different number, the determinant of Q. Of course, they might be the same determinant, but in general, they might not be. Well, actually, what can we say about the connection between the determinant of Q transpose and the determinant of Q? Do you remember how the determinant of a matrix and its transpose are related? They're the same. The determinant of a matrix is equal to the determinant of its transpose. So actually, they are the same determinant. Okay, so maybe I'll just say because the determinant of any matrix, any square matrix, is the determinant of its transpose. Okay. So this is just the determinant of Q squared. And the determinant of Q transpose Q, what is that? Well, Q transpose Q is just the n by n identity matrix, and the determinant of the n by n identity matrix is 1. So we see that 1 equals the determinant of Q squared. And since that's true, the determinant of Q must be a number whose square is 1, so it's either 1 or negative 1. So for instance, you can take, say, the n by n identity matrix. Yeah, I just drew the 2 by 2 one. That's determinant 1, and if you change this bottom right number to negative 1, that's an orthogonal matrix with determinant negative 1. So that's another quick way to tell if a matrix is, well, if it's not orthogonal. If the determinant is not 1, then the matrix is not orthogonal. So going back to the second example, if you calculate the determinant is negative a half. So that actually, we actually found 3 ways of showing that this matrix is not orthogonal. Notice that this is not an if and only if statement, right? This is saying that if you have an orthogonal matrix, then the determinant is plus or minus 1. Now we could think about, well, if you have a matrix, a square matrix, and its determinant is plus or minus 1, does the matrix have to be orthogonal? So if you have a matrix, just think of a matrix with determinant 1 or determinant negative 1. Does that matrix have to be orthogonal? Do the columns have to have unit length and be orthogonal to each other? Well, there's a quick way to see that the answer is no. If you take, say, this matrix, this diagonal matrix, 2 by 2 matrix with entries 1/2 and 2 on the diagonal, right? The determinant of this is 1, so this has determinant 1, but it's not orthogonal. As you can check, if you take this matrix transpose and multiply by itself, you don't get the identity. Or you can see that the columns don't have unit length. So orthogonal matrices have determinant 1 or -1, but there are plenty of other matrices that also have determinant 1 or -1. Well, what does that say about orthogonal matrices and how they affect area or volume? If you have, say, a 2 by 2 orthogonal matrix, and you use that and get a linear transformation, that's going to take a region in R2 to a different region, or possibly the same region. It will be some region in R2. And does this matrix distort the areas? No, right? In particular, these orthogonal matrices preserve areas and volumes because remember that if I have a region S in the domain, when I take the area of S and then multiply it by the absolute value of the determinant of A, I get the area of the transformed region. I get the region, I get the output of the region. I get the image of the region under the transformation, the area of that. And if the determinant of A is 1 or -1, then the absolute value is going to be 1. And so therefore, the orthogonal matrix does not distort areas of regions. Okay. But as we said before, I mean, this matrix, this diagonal matrix with column, with entries 1/2 and 2, this also doesn't distort volumes or areas, but it's not orthogonal. Okay. But orthogonal matrices preserve a property that is just as important, and that's the dot product. So the theorem is orthogonal matrices preserve the dot product. And what does that mean precisely? So more precisely, what it means is if V1 and V2 are vectors in Rn, then if you have an orthogonal matrix, an n by n orthogonal matrix, if you take the image QV1 and take the dot product of that with QV2, now I'm going to use this notation for the dot product. This is equal to the dot product of V1 and V2. Okay. So here I'm using this notation for the dot product. Well, the proof of this is not so hard, because remember, how can I write the dot product of two vectors using matrix multiplication? I take the transpose of the left vector to write it as a row vector, right? My QV1 is a column vector, and I get a row vector by taking the transpose. And then you take that matrix, that 1 by n matrix, and then multiply it by that n by 1 column, which is QV2. So I need to take QV1 transpose and multiply that by QV2. And then by my Matrix properties, transpose properties, it's V1 transpose times Q transpose times Q times V2. And now what can we do to simplify this? Since Q is orthogonal, Q transpose Q is the identity matrix. So this is V1 transpose times the n by n identity matrix times V2. And what is that? That's equal to V1 transpose times V2, and that's the dot product of V1 and V2. So what that means is that since orthogonal matrices don't change the dot product, okay, the dot product of the two input vectors must be the dot product of two output vectors. That means that whenever I have something that's defined in terms of the dot product, the orthogonal matrix transformation doesn't change that either. So for instance, lengths and angles are defined in terms of dot products. So orthogonal matrices preserve those also. So what it means to preserve length is that if I take a vector v in Rn and then multiply it on the left by an orthogonal matrix, the length of this vector, the output, is equal to the length of the input vector. Okay, that's what it means for the orthogonal matrix to preserve lengths. And then for angles, the way to phrase it is if you have two vectors in Rn with angle, say theta, then the angle between QU and QV is also theta. Okay, so for instance in R2, if I have two vectors that are at a 45-degree angle with each other like this, so let's say I have U and V, then when I look at the output of multiplication by Q, that's the transformation T sub Q, the resulting U, the result of applying this transformation to U is going to be some vector with the same length as U. And then the angle between U and V must be the same. So if U is here, then the angle, let's see, it looks like maybe a 45, maybe 50-degree angle or something. The angle must be preserved, and so must the length. Oh, this is a Q times V. Q times V and Q times U. Actually, the property of preserving the inner product characterizes orthogonal matrices. So the next theorem says that conversely, any matrix that preserves inner products, dot product, must be orthogonal. And here's one way to see why this is true. The first fact we need is that if you take any matrix, So first, note that if A is any n by n matrix, then if I take EI transpose, so this is the row vector whose first component, whose ith component is 1 and is 0 everywhere else, and multiply that by a matrix A, a square matrix, and then multiply that by EJ, this is actually just the IJ entry. Okay, that's easy to check because A times EJ just picks out the jth column, and then if you multiply that on the left by this row vector, you just pick out the ith entry in the jth column, and that's the IJ entry of A. So that's a useful fact. It'll be used to prove the theorem. So if you have an orthogonal matrix, if Q is an n by n matrix that preserves the inner product, preserves dot product, well, what we want to show is that Q must be orthogonal, right? We're trying to prove that whenever you have a square matrix that preserves the dot product, it must be orthogonal, that Q transpose Q is the identity. Well, if Q is such a matrix, then the length of QEI must be the same as the length of EI, right? Which must be 1. And the length of QEI squared must be 1. And this squared length is the dot product of QEI with itself. And this is the same as EI transpose times Q transpose QEI. So what this is saying is, since I have this matrix Q transpose Q, let's just call that A, I have an EI transpose AEI, and I know it's 1. So therefore, the II entry of Q transpose Q must be 1. Right? So Q transpose Q, I'm trying to show is the identity matrix. We've just proven that the diagonal entries must be 1. Okay, what if I and j are not equal? Well, we know that EI, so if I is not equal to j, then we know that EI transpose EJ is equal to 0, right? And so therefore, QEI dot QEJ must be 0, because Q preserves the dot product. And this implies, again, we can just write the dot product as EI transpose times Q transpose QEJ must be 0. And again, if we call Q transpose Q transpose QA, then I have this EI transpose AEJ, which I know is the IJ entry. So the IJ entry is 0. The IJ entry of Q transpose Q is 0. So now I know that on the diagonal, the entries are all 1, and off the diagonal, if I is not equal to j, all the entries are 0. So those two facts together imply that Q transpose Q is the n by n identity matrix, and so Q is orthogonal, because that's what orthogonal means. Okay. So now we have 3 different ways of characterizing orthogonal matrices. One is that A transpose A is the identity. The second way is that the columns of A are orthonormal. And the third way is that they preserve the dot product. I mean, this one is not very easy to check, right? It's not easy to check that the matrix preserves the dot product. But it's still useful to know this because it gives you some intuition about what orthogonal matrices do. And in the next video, we'll talk about what all 2x2 orthogonal matrices are, and then probably in a different video, we'll talk about orthogonal matrices that are 3x3. Okay, thanks for watching.